Today we are going to find the internal forces in a cantilever beam. We're going to start off with a really simple case, a cantilever beam with a point load at the end of it, and see how we get on. Now, most of my students absolutely hate solving cantilever beams, and I think it's just because it looks a bit out of the ordinary. But in fact, solving cantilever beams is much simpler than solving, say, simply supported beams. And I'll show you how. Let's get to it. So as I mentioned, we're going to solve this simple cantilever beam with a fixed support at A and a point load at B of 20 kilonewtons. The reason that I'm going to say that solving this is easier is because in this case, if we look at our free body diagram, at A we've got a fixed support, and that means that we've got two perpendicular reaction forces, so here AX and AY, and we've also got a moment. But none of these are in the direction of each other, meaning that each equation that I write will not depend on the previous one. So I can do it in any order that I want. As you can see, I have put all of these just in what I am going to say is my positive coordinate system, so a system like this. And that's it, we're ready to solve the reactions. Now, as I mentioned, I am not reliant on any direction here, so I'm just going to start with the sum of forces in the x direction equals 0, with this being my positive direction. And I can see that I've got ax and nothing else in that direction, so ax equals 0. Moving on, I can straight away go to sum of forces in the y direction equals 0, with this being my positive direction. And in this case, I've got ay in the positive direction and 20 in the negative direction, so ay works out as 20 kilonewtons. And the last thing that I'm going to do to find the reactions is the sum of moments around A equals 0, with this being my positive direction. So in this case, AX and AY pass through A, they don't contribute to moment. I've only got that positive moment, MA, that I defined, and I've got a negative moment from that minus 20 times 6 equals 0, and therefore MA works out as 120 kilonewton times meter. Don't forget your units. It's really important to note that I've got units of force for AX and AY and units of moment for MA. Now, before I move on, just because maybe I'm less sure of this, I am going to do a check, and I'm going to check by summing my moments around B. In this case, the 20 kilonewtons of that load pass through B, and therefore they don't create a moment. AX would also pass through B, although it's 0 in this case, and so I've got AY and MA contributing to moment. MA, we calculated, is 120, and AY gives me a negative moment of 20 times 6, and that indeed equals 0, which means that I've probably calculated my reactions correctly. And the very last thing that I want to do in order to create a proper free body diagram is to put in the values. So AX worked out as 0, I can get rid of that. AY works out as 20 kilonewtons, and MA worked out as 120 kilonewton meters. And since they both came out as positive, that means that the directions that I assumed are correct. And once I found the reactions, I can just create a cut and find the internal forces. So let's do that and finish this example. So here, to find my internal forces, I'm going to create a cut. If I look at this whole beam, I can see that really after A, there's no change until I reach B. So I just need one cut between A and B. And so if I draw out my beam, I'm going to have those two reaction forces. So the reaction force and the reaction moment of 120. And I'm going to draw my internal forces at that cut. So I've got N, I've got S, and I've got my moment M. My X goes from here to here, and X is going to be in between 0 and 6 meters. So before I start, what I want to just quickly do is just create a space for my axial load, for my shear load, and for my bending moment. All right, and now we can begin. I'm going to start off with a sum of forces in the x direction equals 0. And in this case, I've got N, that internal axial force, and nothing else. So N equals 0. The next thing that I'm going to do is I'm going to do sum of forces in the y direction, with this being my positive y. And in this case, I've got 20 in the positive direction, and then s in the negative direction equals 0. So s works out as 20 kilonewtons. And I can see here that that 20 is constant. It doesn't matter at what x I am. And the last thing that I'm going to do is the sum of moments. I always do this, as you know, around the cut, with this being my positive direction. And so in this case, I've got the moment at the cut, so m, plus 120 from my support moment, and minus 20 times x. And the contribution of that 20 force changes linearly, as you can see, wherever I am along the beam. So that moment equals 20x minus 120. Okay, so that is the equation for moment. I can see it's a linear equation. Now I'm interested in a few points, so I want to know what happens when x equals 0, and I want to know what happens when x equals 6. So at point A and point B. When x equals 0, I can easily see that I get minus 120 kilonewton meters, and when x equals 6, I can see that I get 120 minus 120, so I get 0 kilonewton meters. And now we're ready to plot everything on these graphs. So in terms of axial force, I don't really have much. It's just a line of 0. I'll just write that as 0. In terms of my shear force, I can see that I go up to 20, and that just remains constant, and it remains constant until I have the 20 from the point load at B pushing down, and then I go back. So this is a constant of 20 throughout, and it worked out plus in my sign convention. The last thing that I want to do is draw the moments. Now, I want to just note here, I, in my cut, right, assumed that my moment went like this. But my moment came out as minus 120. So actually, this is the wrong direction of my moment. Okay, and in fact, my moment is in this direction. Now, what does that mean? It means that it's pulling on the top, so it's creating tension on the top, making the top longer, and it's pressing on the bottom, so making that bottom shorter, which means that the tension side is on the top. So if I want to draw my moment, here I've got 120 on the top, and I go to 0, and this, as you know, is a linear line, so just a straight line from 120 to 0. And that works out as minus in my sign convention. And that's it. I've got all the diagrams. Now, I finished the exercise, right? I found the diagrams that I needed to find. I found the internal forces at any point along this beam. But I want to show you one last thing. I could have started analysing from the other side, so from right to left or from B to A, and then I wouldn't have had to find the reactions at all. And that negates any mistakes that I might have made when finding my reactions. Let's quickly look at how that would work. Now I'm leaving the solution of the diagrams up. I'm using this more like a check just to show this. But in this case, my cut goes from B to A, as you can see here. Now, the distances are still going to be between 0 and 6 meters, only going in the other direction. So the cut that I would draw would look like this. I would have my point load of 20 here. X would go from here to here. And here I have my cut. Now remember, with these cuts, they need to be in the opposite direction but of the same value as the previous cut for this to work. So my axial load would go this way. My shear force would go up, right? And my moment would go in this direction. Okay, and just to remind you, my previous cut, if I just draw that on quickly, which went in this direction, right, had an axial force going like this, had a shear force going like this, and had a moment going like this. Okay, so you can see that they're in opposite directions, because when we close this up, those are internal forces. They have to disappear. Let's quickly look at how this works out and see if it matches onto the diagrams that we already found. So sum of forces in X to get the axial load, and once again I've got nothing apart from that internal force, which therefore works out as 0. So that matches the diagram for axial load. Then if I do sum of forces in the y direction, I've got 20 going in the negative y direction, and I've got S going in the positive y direction and nothing else, so S equals plus 20 kilonewtons, just like I got before, and we can see once again it's constant, it doesn't change throughout. And the last thing that I'm going to do is that sum of moments around the cut. So in this case, my moment is in the negative direction according to my sign convention, and I've also got minus 20 times x equals 0, so my moment at the cut works out to be minus 20x. In this case, when x equals 0, I'm at point B and I get 0. That matches up with what I got here. And when I am at x equals 6, so at point A, I get minus 120 kilonewton meters. The number matches up. Let's just check that the direction matches up as well. So this was my cut. I assumed that this was the moment. It was not the correct direction, right? In reality, my moment goes in this direction. So pulling at the top, pushing at the bottom, tension is on the top side, so on this side here, and therefore I draw my moment on the top side, and that matches exactly with what I got before. The only benefit here is that I didn't have to calculate the reaction forces. So if I had made a mistake in them, it doesn't appear when I calculate my internal loads. So that is a big advantage. And that's us successfully calculated the reactions and the internal forces and drawn the diagrams for axial force, shear and moment for a simple cantilever beam. I hope that wasn't as scary as cantilever beams sometimes come across. So I hope you learnt something, seen that you can solve it in a few different directions, some which come out as easier than others. And that's us for today. So I hope you join me for some more structural engineering. Bye for now.